So the first issue is learning how to apply rules for assigning oxidation numbers as you go through the balancing procedures. The thing that I try to do is show students as we go along in the balancing process how to assign those numbers. There's some basic rules there, but I'm not going to read these. You can read them, but they'll essentially, it's better to show you as we go through the process, and students will adapt to it very easily as we get deeper into this. And then there's the balancing process by the oxidation number. Now, there are other methods used, but this one will be taught, and there's another one adding half reactions. And now, if we have time, I will show you how to do that. Is because you have reactions, half reactions, listed in the appendix of your textbook, and you can take those and define an oxidation reaction, reduction reaction, just add them together, and you'll have a balanced equation. However, it doesn't apply to all of the reactions, so it has a limitation in how many is available. Oxidation is the process of losing electrons, and reduction is the process of gaining electrons. In the balancing process for an oxidation reduction reaction, two events must ultimately occur. We must have a balance of charge and a mass balance. That is the sum, the mass of the reactants equal sum mass of the products. In the balance of charge, the total number of electrons lost in the process must be equal to the total number of electrons gained. So the sum of electrons undergoing oxidation must equal the sum of the electrons undergoing reduction. So you don't gain or lose anything either by mass or by charge. And it's just a natural order of how processes take place. Now, we'll learn as we go deeper into the study and classification of reactions. There are two real general classifications of reactions. One is the oxidation reduction reaction, often referred to as a redox process. And then you have a metathesis reaction, a process. Sometimes it's referred to as a double replacement. In the oxidation reduction process, changes in oxidation state will occur. However, in the metathesis reactions, as you will see in the future, no change in oxidation states occur between elements moving to different compounds in a chemical process. Now, our interest, of course, is within the oxidation reduction type reaction and some terminology that goes with it, right? Let's start with a simple oxidation reduction reaction in which we'll take zinc and iron. This is zinc and copper. If we have zinc in basic standard state neutral form, is written as that form. And we want to react that with copper in copper sulfate, and that will be in aqueous solution, meaning the solvent is water, and that will go to zinc sulfate, aqueous, and then copper will convert to a basic standard state form like this. Now, when we look at this reaction, we have zinc that starts out with a 0 oxidation state. So I'm just going to put a 0 right there. And it goes to a zinc sulfate, or into the zinc sulfate compound, and sulfate in itself is a -2 from your study of polyions. And so we have to have a +2 in the zinc right there. So we're going from a 0 oxidation state to a +2. So you see there is a change in oxidation state. Copper sulfate, well, of course, the sulfate is still a -2, and the copper in this compound must be a +2. Then it goes to copper in the neutral form, as shown by the superscript 0 right here. Goes to a 0 oxidation state. So you can see how the oxidation states are in fact changing as we go through the chemistry. Now, what I typically tell students, this is just a format that I use. I take the oxidation number and that's shown and put it kind of in the bottom of my bracket, and then a +2 down here, and then I'll have a +2 here and a 0 here. Okay? Now, this is where it starts getting kind of tricky. What must the electrons do, gain or loss, in order to go from a 0 to a more positive value? They must be lost. In terms of 0 to +2, that means the reaction between zinc to zinc sulfate lost 2 electrons. Then you look at the copper, and you look at +2 goes from a +2 to 0 is neutral. Something neutralizes those 2 plus charges. So what neutralizes those 2 is the gain of 2 electrons. Electrons are negatively charged, and so we make a note: gain 2 electrons. Well, that's pretty straightforward. Now, the reaction in itself is balanced. Now, the purpose of using this reaction is to illustrate some terminology more than anything, and the process is going on. And the loss of electrons, this, of course, is the oxidation reaction. And this is the reduction reaction right there. Those are processes. Zinc goes to zinc +2 ions in solution plus 2 electrons. Now, by placing the electrons on the product side like that in that notation format indicates loss of electrons, or this indicates oxidation, loss of electrons. Right there. On the other side, copper goes through a gain of 2 electrons. When we put that on the reactant side, meaning that it is undergoing the gain of electrons, plus 2 aqueous, plus 2 electrons go to neutral copper solid. And the placement of those electrons on the reactant side indicates the reduction reaction. Or the gain of electrons. These are referred to as half reactions. One is an oxidation reaction, and the other is a reduction reaction. Those are processes. Now, there are 2 more terms I need you to focus on, and it's called oxidizing agents and reducing agents. Oxidizing agents cause something else to undergo oxidation, and reducing agents cause something else to undergo reduction. So when we are talking about zinc in an oxidation process, it's the opposite term for agent. So zinc in this is a reducing agent. Zinc metal. Now, not the zinc ion over here, that's already a product over here. You find the agents always on the reactant side. You might check mark that so you don't get confused in who's who in the world of ions. And of course, there's only one other to define, and that's, of course, the copper. And that will be an oxidizing agent. See, copper is undergoing reduction. It causes zinc to lose its electrons. Okay, it's an oxidizing agent. It's causing zinc to undergo oxidation. So oxidizing and then you have reducing agent. Now the oxidizing agent is the copper plus 2, not the copper in reduced form. This is the term typically referred to. Oxygen goes to a reduced form, as many people will refer. And so we look at this as, well, what's the oxidizing agent? Well, it's the copper, because see, the positive charges is sucking the electrons off of the zinc. And so that's what the idea is, causing the zinc to undergo loss of electrons in this process. Okay, rewrite the zinc copper sulfate reaction going to zinc sulfate and copper. In this form, as you would guess, this is the molecular form. That is the standard state form. Coefficients in the smallest whole number ratio, and all of the substances are listed in their basic standard state. That is, we looked them up in the back of the book. Trust me, that's the form. Now, I can write a second kind called an equation called an ionic equation. And you'll see more of this when we get over into metathesis, more than you probably will right now. The ionic equation is where you show those ionizable compounds broken into the cations and anions. Here we have the copper sulfate and zinc sulfate, and those can break into the cation copper and sulfate, and this one's zinc and then sulfate, like this. So we can write this plus copper plus 2 and put aqueous on that, plus SO4 minus 2 aqueous, and see how I split those out into that form and show them in that designation like that. And this of course goes to zinc plus 2 aqueous plus sulfate minus 2 aqueous, and then I finish the notations with copper solid, which is the reduced form, which is the outcome down here. Now, sulfate in here is required as what we call a counterion. And you got to have a counterion. This could be any anion to carry the primary cations that are involved in the reaction. So I just happen to use sulfate. These do not enter into the chemical process, and those that do not enter into the chemical process are referred to as spectator ions. Now this one only has one spectator ion, the sulfate. Now I'll show you some that have 2 spectator ions, and some that have none. We'll get to that in due time. But if the ion doesn't enter into the reaction, it's referred to as a spectator ion. When you mentally, of course, cancel those out, because one's on the left of the arrow and one's on the right of the arrow, and you cancel those out and rewrite your equation, what you have is the net ionic equation. No spec ions listed, just as a reference. So this would be zinc plus your copper plus 2 aqueous going to zinc plus 2 aqueous and plus the copper reduced form. So those are the forms that you can write in these equations as you go through. So the ones I'm going to introduce you to in balancing oxidation reduction are going to be ionic equations. So the molecular equations work like that, but I've taken out all of the spectator ions so they won't confuse the issue. Make it hopefully easier for you. Okay, follow me along in the handout that I gave you on balancing the oxidation reduction. And so you can kind of keep that off to the side to see how this is, because it's going to be repetitive all the way through this. Okay, it starts out by saying assign oxidation numbers, and that's assigned to the individual elements. Now right now, until I tell you different, oxygen is always -2 and hydrogen is a +1. Yeah, there are cases, and strange, you'll see one in the next example that is off the charts. I may not even use that. Okay, so the elements by themselves with an oxidation state listed is the oxidation state. So I'll just put that up there as a +2. Oxygen, like I say, is a -2 individually, but I have 3 of them, so the net charge or the overall charge is a -6. See what I did? Now, -6 plus whatever you put over here must give you a net charge of -1. So what would you have to add back to a -6? Well, of course, that's a +5. So it's a deductive process in assigning the collection of oxidation numbers. Now you're over here with manganese, the permanganate ion. And so oxygen is a -2, and 2 times 4 is a -8 net. And so what would I have to add right here to get a -1? +7. See what I'm doing? Everybody good? And then bismuth is already listed as a +3. Okay. This would be the sum of the individual oxidation states. Okay. Oxygen I indicated was a -2. Now that gives you a little simple algebra equation. And so when you solve for the manganese, it would be a 8 minus 1 or plus 7. See how that goes into it like that. So, does that help, man?
Yes.
Okay. Now, like I showed you in the notation when I was defining the different parts of the oxidation reduction reaction, I will look for what has undergone changes in oxidation state. Determine change per atom is what it's showing here. So I look at manganese is undergoing a change, and so I'll make a bracket for that one, going to a +7. And then bismuth is going from a +5 to a +3. Now for any oxidation reduction reaction, keep in mind there's always just one oxidation and one reduction. You don't have multiple oxidations. Now I will show you before we leave the thing called disproportionation, where one element provides both the oxidation and reduction elements in the generation of the product side. But that's not what I'm saying, in that you don't have 2 or 3 oxidation reactions, 2 or 3 reductions. There's only one undergoing oxidation reduction ever in these processes. Okay, so this would be a +5 going to a +3. Now, determining what the changes are, look at, you're going to a more positive direction. That indicates a loss of electrons, which means a lost 5 electrons. And 5 to 3 means you gain 2. Electron. Okay, everybody still with me? Now, in the balancing of oxidation reduction reactions, 2 events must occur. 1, you must have a balance of charge, and 2, you must have a balance of mass. Always balance the charge first. Then you'll finish with balance of mass. So we'll continue in the charge. So if I have a 5 up here and a 2 here, I've got to make those equal. So what you can do is multiply this one by 2 and this one by a 5. Now this is where it gets tricky for the student. Now you agree that that makes sense as far as making the 2 lines equal. Everybody good there? Now it's the way you think about these processes that will make sense and will make the reaction and the processing make sense. What you're saying here, each bismuth is losing 5 electrons, and each manganese, each manganese is losing 5 electrons, and each bismuth is gaining 2 electrons. But to make this 2 equal, you need to say in your mind 2 manganese each lost 5 electrons. So you got one spitting out 5, another spitting, what's the total? 10. So that's what you have, 2 manganese each losing the proper number of electrons. So I'll need a 2 here and a 2 here. You have to have that, because on the other side of this coin you have 5 bismuths, 5 bismuths each gaining 2, 5 of them. So I have to have a 5 bismuths gaining those 2 electrons. That's a total of 10. So, and then over here you wind up with 5 also. Now, it's the way you think about how many do you need gaining electrons on the oxidation process, and how many of those elements you need losing electrons on the reduction oxidation process versus the reduction process, what I'm trying to say. That makes sense. And it gets a little tricky here, and that's the simplest one I got right there. Then, once you get the charge balance, then you go to mass balance. And what it says, if there are other elements within the structure, whether they be spectator ions or not, that undergo changes, then you balance those. There may be some that aren't undergoing oxidation reduction, and you have to balance all of those. Well, I'm not going to have any of those right now. So once you get to here, you're ready to go into mass balance. Well, everybody's balanced. Look, you got 2 manganese, 5 bismuth. So what's not balanced?
Oxygen.
It's the oxygens and hydrogens. So if you look down there at the bottom of the list, it says balance the oxygens first, and then it's got a little set of rules for balancing hydrogen. So here's what you remember. When you get the charges balanced and the mass balance on all the other stuff, and you go into oxygen-nitrogen balance, balance always the oxygens first, and then finish with hydrogen. Always balance oxygen first, and then finish with hydrogen. Everybody here? All right. So we need to balance the oxygen. So I'm going to kind of split this into reactant and product kind of partition. Okay, on the left side I have 15 oxys. And on the right I have 8 oxys over here. So I need 7 oxys on that side. Is that right? Okay. So what does it say to do here? If it is an acidic or neutral system, add, well, it should be a capital H, you know, H2O to the side needing oxygen. So all you do is come in here, and so therefore add 7 H2Os to that side. And to the other side, you add an equal amount of hydrogens to balance it out. Coming down here. Well, you got your oxygens balanced when you do that. And then to balance your hydrogens, well, you got 14. And so you don't have any hydrogens over here, so I need to split that. So over here I've got 0 hydrogens. Okay, so I need 14 H pluses over here, and you're given 14 hydrogens on that side, so we've got to add those 14. Now, a couple of ways to do this. A lot of times I'll put just the plus 14 hydrogens over the arrows, indicating that they're going into the reaction as much. Sometimes 14 hydrogens, just put them in at the end, and you can recheck your balances. Now, it'll tell you at the end, simplify hydrogen, hydroxides, and waters. And if we have time, we'll use that over the base side. I'll show you how that works. But you'll have, say, a bunch of H's, waters over here, and OH's and hydrogens, and then the same thing. And you have to combine those. I'll show you later. I'm catching. Okay. The point in this equation is between the chlorine, Cl2, and against the chloride right here. Okay, you cannot ignore the subscript in this in terms of your electron transfers and your balancing and what have you. And I'll show you. So we'll follow the procedures in assigning oxidation numbers. Oxygen's always a -2, and that's a -6. And so I'd have to have a +5 here to add back to a -6 to get a net -1. This is already a -1 because it's listed as such. Chlorine in basic standard state is a 0 oxidation state, is neutral. And ClO -2 -4, and so this chloride in here is a +4. Okay, so we looked at what's undergone changes in oxidation states. So here we've got to find an oxidation and a reduction in the process. So just okay. Well, you've got chlorides and chlorines and all over the place here. You want to find an oxidation combination and a reduction combination. If I went here to here, that's 5 to 0 and -1 to +4. Okay, it's not going to work out. So it would kill itself before you even got into the problem. So this would be a +5 and a +4 and then a -1, and it's neutralizing. Now you make your choices of gains and losses per element first, and then you apply multiples. That's where the subscript 2 comes in. We cannot ignore the subscript 2 at this point. Here in this one, we go from +5 to +4. That's a gain of 1 electron. Everybody good on that? In this one, -1 to 0 is going to a more positive end, so it lost an electron per element. Now this is where you have to maintain the subscript 2. So in generating this, listen to me carefully. In generating a Cl2, how many chlorides do you have to have? 2. Got to have 2. So you're forced into this by default, so to speak. Everybody see what I'm trying to emphasize here? You're forced into that. Now you start balancing your charge after that. And so we have, I'm going to move this over just a little bit. I'll put that over here. So now we want to balance against that. Well, that's 2 lost, 1 gained, so I got to double this to get that to match. So I've got 2 chlorides, each gaining 1 electron. You see what I did? I could not put a coefficient here because it already it was defined by the subscript that was in the beginning of the reaction. But you can't ignore those subscripts. Okay. So we've got to balance the charge now. You don't go any further than if it balances, it balances. So now everything's balanced except the oxygens and hydrogens as we go through this. It's an acidic system. You have to be told that it's either in a basic or an acidic system. Then 2 to 3 is, well, over here we got 6 oxys. And over here we've got 4 oxys. So we need 2 oxys. So it says add 1 water per oxy needed. So we need to add 2 waters over here on that side. And then to balance the hydrogens, we've got now 4 hydrogens on this side, and we have 0 hydrogens on this side. So I need 4 H pluses, and so I add that over here. Okay. Well, those are pretty straight up stuff. But you have to get used to dealing with little subscripts and that you can't ignore in the balancing process. Now the first one in this collection is the MnO4, negative plus C2O oxalate, and that is going to MnO2 plus the carbon dioxide. Okay, so in the majority of the effort, you use the same rules for balancing your charge. It's when you get into the oxygen-hydrogen balance that we have to pay close attention to the order of what is being added and where. So, starting out, this would be a -2, -8, +7, just like in the example we used in the previous one, but this was a -2, -8, and so what would I have to add to a -8 to get a -2 net? I would have to add a +6. Well, if I've already got 2, then that means each one's a +3. Everybody good on that? So I kind of start with the oxygen at -2 and then work my way back to the carbon as a +3. Now oxygen again is a -2, -4, and this one goes to a +4. And O2 is -2, -4, +4 on the carbon. Now, so this is why I just work through the oxidation states, because people usually pick it up pretty quick on that. Everybody good on that one? Any questions? Then we pick out the changes and just follow the same rules that we would follow for acids. Again, you don't really see a wrinkle in the procedure till you get to the oxygen-hydrogen balances toward the end. So this is a +7 going to a +4 and a +6 going to a +4. So you want to be accurate in your bookkeeping. Now identify what's going on. So this looks like 4, 5, 6, 7. We gained 3 electrons, and so that's your reduction reaction. What's the oxidizing agent? Well, it's the MnO4 over here, just to review that term. And then your C2O4 will be the reducing agent. So the individual structures or compounds will be the agents, but the process is oxidation reduction. So there's a difference, so check mark that. Okay, 6 to 4. Wait a minute. You can't do that. No, +3, sorry, not 6. Duh. Anyway, 3 to 4. Lost 1 electron. Yeah, you can't have 2 reductions. A good example. So now you have to balance these in terms of charge. Well, you've got 2 carbons down here and 1 back over here. So if you're kind of going from 2 over here and 1 over here, that means you've got to have an extra one on the right side. So just like the last problem we worked, you're forced to include another carbon on that product side, because see, the subscript defines the oxalate. You can't just toss the subscript. And so by defining that as oxalate, C2, you've got to put another one over here, and then you come down here that you have each carbon is losing an electron. See what I did? Everybody good? No questions. So you got to be careful with that. Okay? Because if you see 1 over here, 2 over here, 3 or 4, there are those that you've got to make those numbers come out mass while you're still transferring electrons. Okay, I got a 3 against a 2 here. So this is going to require a bracket. I usually put a little extra brackets around, again, because I'll have to balance this. This is 1. I got 1 manganese gaining, see, it's 1 and 1 on each side now. So each 1 manganese gains 3 electrons. And that's it. But I've got to have 3 of them because, no, I've got to have 2 of them, excuse me. 2 of them here, and which amounts to 6 electrons. You be careful and don't get confused. I've got to have 6 electrons lost also, so that requires a 3 in here. So I'll come in here with a 3. Now look, okay, and so I've got to come in here with a 6. See how I changed this? Like that. I don't have a subscript. There is no subscript there, but you still have to maintain the numbers of elements undergoing delivery of charge or absorption of charge. So you started with 2 turning into a 1 turning into a +4, but you have to have 2 of them, so we put the 2 in here. But I had to come in with a 3 to make total of 6 electrons bouncing around here. And that's where I put the other 3 here. I couldn't get rid of the subscript, but over here I still have to conform to the 6th carbon. Please study that, because it is vital that you be able to connect those 2. You don't lose or gain elements. And this is an example where you're forced into changing coefficients to match each side. This one's a 3 and 6. I hope you see that. It takes some look-see. Look at it again when you get home. Be sure you understand that, because I will be putting one of those on the exam, so you can count on it. Hint, hint. Now, I'm not going to do that on a quiz or something like that. And what I usually put on a quiz is, how many electrons are gained, how many electrons are lost, or something like that. That's about it. But do study this. Okay, I'm going to work. We're not through with it. Okay. So now everything's balanced charge-wise. Now we need to get the oxygens and hydrogens. So that's 2 to 6 is 12, 30, 40, 50, 16 oxys here. And over here, 3 to 4 is 12 and 20 oxys. Looks like. That's 8 and 12, that's 20. So over here I need 4 oxys. Well, there's a special procedure in an alkaline system. Let's look at that rule down there. Now listen to it carefully. To the side needing oxygen, for balancing oxygens, add 2 hydroxides per oxygen to the side needing oxygen and half as much to the other side. That's squirrely. I'm going to show you a shortcut here in a second. And then when you go to the hydrogens, you balance the hydrogens first with water and then finish with OHs. All right, this is what I show students in balancing the hydrogens and oxys. If you'll understand what I'm just about to write. 2 OHs, you got to start with hydroxides. And then you finish with H2Os. And I usually partition it like this. And this is the oxy balance. And then you start with water and finish with the OH. Notice how the OHs are on the outside. Everything is OH, H2O, H2O, finish with OH. But the first one is 2, right there. This combination is a hydrogen balance. Okay, watch what I do here. To the side needing oxygen, I need to add 2 hydroxides per oxygen needed. Well, I need 4 oxygens, so I need to come over here with 8 hydroxides. That's what it says do. To the other side, I add half as much water, so I come over here with 4 H2Os. Now, you can add them up. You can check your oxygens now. The hydrogens may or may not balance, but you know your oxygens will if you do that. If you can mentally see this OH, H2O, H2O, OH. because the first two balance the oxygen, and then the second two is the procedure for balancing the hydrogen. But don't forget to put a 2 out front of it, because that's the side that needs oxygen. You got to add 2 hydroxides per oxygen needed to the side needing oxygen. Then half as much water on the other side for oxygen balance. Then it's 1 and 1 for this. So if we check this out, we've got 8 hydrogens and 8 hydrogens, so I think that everything balances out in that equation. Once you get the coefficients set and everything balanced, look on the left and look on the right. If you have OHs and H's over here and H2Os and OHs, where they'll cancel each other out. That's what they're talking about, simplifying. Because you may have OHs on both sides or waters on both sides in the process of balancing. Because see, you're using water and OHs and water and OHs, and some problems come out with extra on each side. Well, if you have hypothetically 8 hydrogen H2Os over here and 6 H2Os over here, this will cancel and revert to 2 H2Os, and it'll still stay in the balance, but it will be required that you simplify the left side and the right side. Make sense? And it's just a little sidebar in there, because you work some of these problems and you'll probably find one mixed up in there. I just don't have the time to work them all for you.